All right, so let's see this particular question now. So in this question, we are given an integer array, right? And it is also given that in this particular array, no two adjacent elements are same, right? Now what we need to do is we need to find the index of a peak element, right? And the definition of a peak element is that, number can be a peak element if it is greater than its adjacent elements, right? Like both the left and the right elements, if they at all exist, right? And if there are multiple peak elements, then we need to just return the index of any one of them, right? So essentially what they mean to say is that if you consider this particular input array, for example, if you take the case of 7 over here, right? So 7 is greater than 5, right? But then 7 is actually lesser than 8. That means 7 is not the peak element over here, right? Similarly, now if you see the case of 8, then 8 is greater than 7 and 8 is also greater than 3. That means it is greater than both its adjacent elements, and that's why this is a peak element, right? And now there can be multiple peak elements, that is a possibility. So in that case, we can just return the index of any one of the peak elements in this entire array, right? So that's what we need to do. And also they have given a condition over here, a note over here, that the element before the first element and the element after the last element can be considered as negative infinity, right? Which essentially means that in case of the first element, if the first element is actually greater than the second element, that means the first element can be considered as a peak element, because I mean any number will definitely be greater than negative infinity, right? So we just, in case of the first element, we just need to compare it with the second element. And similarly, like in case of the last element, if this last element is greater than the second last element, then automatically it will become the peak element, because again the element next to the last element is negative infinity, and definitely this number will be greater than negative infinity, right? So those are the two corner cases that we have to check. In case of the first and the last element of the array, we just need to compare it with the the next element and the previous elements respectively, to figure out whether they are the peak elements or not, right? So that's the entire question. Now in this input array, if you see, 8 is the peak element as we saw, and the index of 8 is 0, 1, 2, 3, 4, 5, right? That's why our output is 5 over here, right? So that's what we need to do in this particular question. Now maybe you can just pause this particular video and try to think of a solution, and once you are done, you can just come back and check the solution. All right. So now to solve this particular question, see what we can do is we can actually apply binary search over here, right? So like our stopping condition and the condition to actually move towards the left or the right would be a little different over here. But essentially what we can do is, first of all, we will find the mid in this initial array, right? So the mid over here in the original array will be 5, right? Now what I will do is I will figure out whether this mid at any given point in time is actually a peak element or not, right? So if it is a peak element, for this to be a peak element, it has to be greater than the previous element, and it also has to be greater than its next element, right? Now 5 clearly is greater than the previous element, but it is lesser than the next element, right? That means 5 is not the peak, right? And I have to now either move towards the right or I have to move towards the left, and then again apply binary search over there and again find the mid, right? Now on what basis I will decide whether I have to move right or towards the left? I will see, for a fact, if I move towards the right, I know for a fact that I have one number over here, at least one number over here, which is greater than its previous number at least, right? So I just need to figure out whether it is also greater than its next number or not, right? So the possibility of having a peak in the right half is actually more, right? Because I already have one number over here which is actually greater than its previous number, right? So that's why I will always move towards that half of the array where I have the number greater than the current mid, right? So if my right number is actually greater than the current mid, then I will move towards the right half. If my left number, that is the previous number, then the current mid is actually greater than the current mid, then I will move towards the left half, right? And if both are greater than the current mid, then I can move in the either of the directions, in either of the parts. That is fine. I can always fix that if both are equal, I can just go to either the left half or the right half. It won't matter, right? So now, for example, if 5 is my mid, now we saw that 5 is greater than 4 but less than 7. So now I will go towards the left half, right? So now my L will be over here. I will do L equal to mid plus 1, right? So now my L is over here, R is over here. So now mid will be 8. Now again, I will check if 8 is my peak element. Now if you see 8 is greater than 7 and 8 is also greater than 3. That means 8 is my peak element, and now I can return the index of this current mid, which is 5, as my output, right? That's what I can keep doing. And if you talk about the time complexity now over here, it will be order of log n, because I'm every time dividing my entire array into two equal halves, right? And then I'm doing constant time operations, so it will be order of log n. And if you talk about space complexity, since we are not using any extra space over here, it will be constant, it will be order of 1, right? So that's the entire intuition behind this particular problem. That's how we solve it. And now maybe let's jump to our IDE and code this particular solution. All right, so now let's implement the solution that we discussed. So to start with, let me just, as usual, declare a function. I will call it as peak element, like this, right? And this will accept an integer array, ARR. And now, first of all, what I will do is I will just capture the length of this particular input array in a variable n, right? Like this. And now I will just declare and initialize my left pointer to 0 for binary search, and declare and initialize my right pointer to the last element, which is n minus 1, right? This is something what I will do. And also, like before actually initializing these, what I can also do is I can just check if my length of the input array is equal to 1, right? So if it is equal to 1, it would mean that there is no element on the right side and no element on the left side, right, of the only element that we have in the input array, and it would mean that it can be considered as the peak element, right? Because as we know that the number next to the last element is negative infinity, and also the number previous to the first element is also negative infinity. So this number, the only number that we have over here would be the first number also and the last number also, right? And that's why numbers on both the sides of this only element in the array would be negative infinities, and that's why this particular element will automatically become the peak element, right? And hence I can just return 0 over here, because 0 will be the index of the first element, right? The only element that we have, right? That's why we are just checking this particular condition as a corner case. And if that is not the case, if length is greater than 1, then we can just go on and continue with our binary search and declare and initialize the left and the right pointer, right? So that's what we are doing. And now what I can do is I can just run a while loop with this condition for binary search, that while my L is less than equal to R, I will just keep finding the mid by this particular formula, right? L plus R divided by 2. And then what I will do is, see, first of all, I will handle the corner cases, right? Where either my mid, that I have found over here is actually equal to 0, or my mid is equal to n minus 1. That is, my mid is actually the first element or it is the last element, right? In these two cases, I just need to compare, the current element at the mid with either the next element or the previous element, right? I just need to compare it with one element, right? So that's why I will just, handle these cases first. So I will just say if my mid is equal to 0, then in that case, I will just check if my current mid, like the array of mid, is greater than array of mid plus 1, right? And if that is the case, then I can say that my mid is, the current mid is actually the peak element, and I can just return the current mid index, right? And if that is not the case, then it means that, the array of mid plus 1 is actually greater than array of mid. That means the right element is greater than the current mid, and so I should now do the binary search on the right half. So I will just increment my left pointer to mid plus 1, and I will move towards the right half of the array, right? And if this is not the case, if mid is not equal to 0, then now I will check if my mid is equal to n minus 1. That is, if it is the last element, right? So in that case, again I will check now if my array of mid is actually greater than array of mid minus 1 this time, right? Like this, right? In that case, now I will return mid, right? And if that is not the case again, then now I will move towards the left side, right? Because now this would mean that my array of mid minus 1, that is the left element, is actually greater than array of mid, right? That's why I will move towards the left part of the array and apply binary search over there. So that would mean I will do array equal to mid minus 1 now, right? Like this. And if That is also not the case. If my mid is neither equal to 0 nor it is the last element, then it is somewhere in between, right? The mid. And so I will have to check, I will have to compare it with both the adjacent elements, that is the previous element also and the next element also, right? So I will put the condition over here for that. I will say if my array of mid is actually greater than array of mid minus 1, and also my array of mid is actually greater than array of mid plus 1, right? In that case, I will just return mid because that will be my peak element, right? The element at the current mid will be my peak element, right? And if that is not the case, then now I need to move to that side where I have a greater number than the current mid, right? So if my right number is actually greater than the current mid, then I will move towards the right side and do binary search over there. If my left number is greater than the current mid, then I will move towards the left side and do the binary search, right? So for that reason, now I will check if my array of mid is actually lesser than my array of mid minus 1, right? That is the previous element is greater than the current mid element at the current mid, then I will move towards the left side, right? And I will do r equal to mid minus 1, right? And if that is not the case, if my array of mid is actually greater than the previous element, it would mean that the right element, the next element to mid is actually greater than mid, right? And so I should move and do the binary search on the right half now. So that's why I will do L equal to mid plus 1 like this, right? So I will just keep doing this till I hit this particular condition, till my L becomes greater than R. I will keep doing this and I will just return the mid wherever I find a peak element. And if I do not find a peak element at all in the entire array, I will come out of this particular while loop and I will just return minus 1. That means there is no peak element at all in this entire array, and it would mean that minus 1 would mean that the peak element is not present basically, right? So this is the entire solution to this particular problem. I hope you understood how we are making use of binary search over here to solve this particular question in order of log n time, right? And the space complexity, as we discussed, and as we are seeing that we are not using any extra space over here, it will be order of 1, right? So that's the entire solution to this particular problem. And now I will see you in the next video. Thank you.